was behind the rising sun. I told her, don't be uneasy, because I'm behind that atomic bomb. Nation after nation was here and far away. Nation after nation was here and far away. Well, they soon got the news, and there where they would stay. Over in Japan, you know they let down and cry. Over in Japan, you know they let down and cry. And poor Toto had to find a place to hide.
Well, good evening, everybody, and welcome to the last week of the semester. This is lecture 38 for Physics in Everyday Life and Conceptual Physics. And today we're going to talk about nuclear weapons, which may not be something you've thought a lot about. It may not be something that you clearly have everyday life experience with, but they are a reality of the time we live in. And I think it's important for us as informed citizens to know what the heck a nuclear weapon is when we decide whether we are for or against them when that matter comes up in our national political debate. So last time we talked a little bit about simpler devices, I suppose, music storage devices such as iPods, but now phones and the like. And all modern electronics basically operate on a whole series of transistors. Transistors are the networks that store and process information in computers and in solid-state hard drives and flash memory and things of that nature. Transistors have 3 or more layers of semiconducting material, and current flows through a transistor when the gate, if you will, is opened by a current flowing in yet another electric circuit nearby. And then storing this information and processing this information comes under the domain of Boolean logic, which is a series of mathematical rules that are used when you want to combine ones and zeros and process information in a binary form. So as I said, we want to talk a little bit about nuclear weapons in today's lecture. And if you, I don't know, I'm assuming that everybody has had a course in which you studied World War II and are aware of the fact that World War II, between the United States and Japan at least, ended when the United States dropped 2 atomic bombs on Japan in short succession. And so again, I'm not here to argue for or against the issue on one side or another of it ethically or anything like that, but simply to make you aware of what the physics are that are behind a device such as those that were used. And so to jog memories or perhaps to introduce new information to you, this is a brief clip from the, I believe it's from the BBC.
On August the 6th, 1945, 2 American Super Fortress bombers arrived over the Japanese city of Hiroshima on the world's most devastating military mission. The Enola Gay, with Colonel Paul Tibbets at the controls, was about to drop the first atomic bomb, a weapon conceived by a group of international scientists based at Los Alamos in the United States. So far, no one knew exactly what effect the bomb would have, either on the unsuspecting inhabitants below or on the crew of the plane itself. They were soon to find out.
As soon as the bomb went off, the whole inside of the airplane just lit up as if someone had set off a flashbulb. And then we had to wait, and this was our big worry, is what would the blast do when the blast got to the airplane? And finally the blast did arrive. It was like being in an ash can and getting someone kicking. And then we crowded to the window and saw just the whole city completely covered in smoke with this very tall mushroom cloud rising from it.
President Truman had already threatened the Japanese with a rain of ruin from the air, the like of which has never been seen on this earth. When the truth was revealed, his words seemed an understatement. Buildings vaporized, so did the clothes on people's backs. Was it a bomb that should never have been dropped? Some people thought so. Others argued that it shortened the war and kept the subsequent peace. One thing was not in doubt. Hiroshima taught mankind the awful truth about nuclear weapons and just what horror they could bestow.
So what is a nuclear weapon and how does it work? Well, a nuclear might bring to mind the word nucleus, and that's in fact where we want to start this discussion. So what's in a nucleus? Recall that we've talked about this several weeks ago, but you might want to jog your memory here if you got a piece of scratch paper. You know, what does an atom look like if you just sketch a picture of an atom? And what are the parts of that atom, the subatomic particles as they're referred to? Where are they located? Cosmologists, who are scientists who study the early structure of the universe, think that the early universe was mostly filled with just hydrogen. And so that's another good question. If you've ever studied the periodic table in chemistry, you know hydrogen is that one that's up there in the corner. It's the simplest element that we have. If the early universe was just hydrogen, where did all the rest of this stuff come from? The stuff that's making up you, me, the computer we're watching this on, the air around us. What does a hydrogen atom look like? Finally, let's think a little bit about the nucleus of the atom, because that is where the essence of the nuclear weapon comes from. What particles are present in the nucleus? What are their charges? And what does this suggest about any forces that are present in the nucleus? If you've forgotten any of this stuff, you can look back at lecture 25, where we talked about the concept of static electricity, or if you Google structure of an atom, you'll probably find something fairly quickly. But we're going to ask a couple of questions just to see if you jogged your memory on this, or if this is something you knew. Atoms are comprised of which three subatomic particles? Electrons, neutrons, and photons, electrons, neutrons, and protons, neutrons, photons, and protons, or electrons, photons, and protons. Again, you can answer these questions on the Poll Everywhere survey. It's linked in the lecture folder. It's also linked with the image on this slide if you're following along in the Google Slides. A second question. So what statement regarding electrostatic forces in the nucleus is true? Is it that electrostatic forces cause protons to attract neutrons, protons to repel neutrons? Do they cause protons to attract other protons, protons to repel other protons, neutrons to attract other neutrons, or neutrons to repel other neutrons? So every possible combination of proton and neutron, and attract and repel are your options there. Well, inside the nucleus, there are a bunch of protons and neutrons, and collectively they get called nucleons for folks that are doing nuclear science. And so the artist's depiction at the right is a sodium nucleus consisting of 11 protons and 12 neutrons, but collectively that would be considered 23 nucleons. Neutrons and protons are both very, very small. Nobody's ever seen them. They're beyond the limits of optical devices to see, but our model tells us they should be somewhere in the neighborhood of 10 to the minus 15 meters in diameter, which is very, very small distance. Then you have this other problem in the nucleus, and that is protons are thought to be positively charged, and neutrons are electrically neutral, so they don't really interact with anything electrically. But if you put more than one proton in the nucleus, they both have positive charge, and they should repel each other. and push each other apart. And that is the case. Protons will repel other protons. But if they're being held together in the nucleus, that must mean that there is some other thing holding them there. So this is always one of the places where it feels like made-up physics to me, because nuclear scientists say, okay, there must be a strong nuclear force. Well, yeah, that's true. If the nucleus is staying together, electrically, if it would get pushed apart, there must be some other force that is stronger than the electrostatic force that's holding the nucleus together. It gets the name strong nuclear force. Some folks in physics are actually working on something called the grand unified theory, where they're trying to explain how all of these variety of forces, gravitational forces, electric forces, strong nuclear forces, weak forces, are all one and the same kind of force. Nucleons in the nucleus are thought to move around, so the protons and the neutrons are moving, and as you'll see in the simulation we're going to look at in a little bit, they're in motion. Quantum mechanics actually tells us you can't actually know exactly where they are, but they're in the nucleus, and that's all we need for this particular discussion. And then if you get one or more of these nucleons to move outside of the range of the strong nuclear force. So strong nuclear force is a strong force, but it's a very close range force. So it holds things together when they're packed tightly together. If they get a little bit further apart, that strong nuclear force gets weak really fast with an increase in distance. And so a nucleon may be ejected from the rest of the nucleus, and in the process of doing so, release some energy. So this is a simulation on the PhET website dealing with radioactive decay, and if you want to play along with it, the link is there. It's also in the announcements. This is another one of the older Java-based simulators, so I actually went and played with this and made a little movie of it earlier this afternoon. So I'm just going to show you what this simulator does. It starts out with, if you do the single atom tab, a nucleus of polonium, and that polonium has 211 nucleons, which is what the little 211 there next to it means. But polonium is also nuclearly unstable. In other words, after a while, a polonium nucleus will on its own break apart, and it turns out to eject something called an alpha particle, which is 2 protons and 2 neutrons. That alpha particle flies off, and now the nucleus is 4 less nucleons, so it becomes lead-207, and you can see that briefly here in the simulator before I hit the reset nucleus button and start it again. Furthermore, I can't know when this is going to happen. Sometimes it happens really quickly, sometimes it takes a long time to happen. The time when this nucleus transitions is fundamentally not something we can know. This is the same simulation, but now I have a bucket of polonium. So here's 10 polonium nuclei, for example. And you'll notice that as the simulator starts, some of them undergo this radioactive decay really quickly, others not so quickly. And so right now we got a couple of leads, or poloniums rather, that are holding out. Still one polonium, but 9 have become this lead-207. Eventually all of them will decay into lead-207, but not all at the same time. And it turns out we can't know when an individual nucleus would decay. Nobody's actually figured that out, if that is indeed knowable. But we do know pretty well the characteristics of materials like polonium or other radioactive materials if you have enough of them together. And so you can characterize it that way. So here's a whole bunch of poloniums decaying into lead. And again, most of them happen early, but there's always a few holdouts in here. What you can characterize about this system is the time it takes for half of them to undergo this radioactive decay process. And we'll talk more about that concept here in a minute with the concept of half-life. So here is the simulation that you can do. If you happen to have some coins lying around your house, you can do this with actual physical coins. That might take a little more time, but if you like to do stuff hands-on and play around with it, go ahead and do that. Alternately, you can use simulated coins. And so on this slide, there's a link to a website that gives you simulated coin flips, and you can choose however many coins you would like to flip simultaneously. For the purpose of this experiment, we're going to assume that all of our coins start in the head state. So if you choose to start with 50 coins, like is recommended, you start out with 50 heads. So I have a whole bunch of 50 heads is representing 50 undecayed nuclei. Then I flip them all, whether I do it virtually or reality. Well, they're not all going to come up heads, and they're not all going to come up tails. Some amount will come up heads. And so whatever is heads after a flip remains an undecayed nuclei in my simulation, and everything that comes up tails is decayed and has turned into something else and gets discarded for the rest of the game. Then you take the remaining heads, you flip them again, you see what number of them are undecayed after another flip, get rid of the tails, and you keep repeating that process until you're left with no heads left, which would symbolize a time when all of your nuclei have undergone this nuclear decay. I've made a Google sheet, and so you can actually just go ahead and copy your data into that, and as you do so, it'll generate a graph of what this looks like in terms of our modeled number of undecayed atoms as a function of time. If you're curious to see what I got when I did the same thing, there's a tab on that Google sheet that has my results in there as well. Now, this is a two-state system, and so it has a certain characteristic curve, but you can do this same simulation with lots of things. So if you happen to have a whole bunch of dice, you can do this with dice, and you just say it decays every time. Well, if you want a low probability of radioactive decay, so mimicking a system that has a long time before it radioactively decays, you just say like, okay, every time the dice show up 1, they've decayed, but a 2, 3, 4, 5, and 6 stays in the game. And you'll see that it takes a longer time to get all of your dice out of the game if you do it that way. So half-life is the number that we actually use to characterize a nuclear system that undergoes radioactive decay. So again, we can't know when a single atom is decayed, but you can actually fairly well predict the characteristics of a large ensemble of these things. And again, it's very rare to have just one nucleus, right? We're usually studying systems where we have billions and billions of nuclei. And overall, then, the behavior of the large ensemble system is, in fact, highly predictable. And it's predicted, or it's characterized, rather, by a number called half-life. Half-life is the amount of time it takes for half of those atoms to undergo a radioactive decay. And so if you plot the number of atoms that remain undecayed as a function of time, here I've done it in a fractional sense, then you get this curve that is a graph of radioactive decay, but can also be used to find half-life. So I started out with 100% in both my red and blue systems, and then they both underwent a at least simulated nuclear decay here. But blue, you'll notice the fraction of blue dropped off much more quickly than the red one did, which tells me that blue has a shorter half-life than the simulated red material. You can find this half-life off of the graph. If you just sketch a horizontal line at the 50% mark, you see that that crosses the blue curve at least the simulated time of 3 years, and that crosses the red curve at the simulated time of 15 years. So in this hypothetical example, the red material has a half-life that is 5 times longer than the blue. And so I would expect if these were two radioactive samples, I would have red around for a longer time than I would have blue. You can mathematically characterize this as well. We're going to think about this mathematical relationship in this particular discussion, and then actually do a problem-solving question with it in Wednesday's lecture. So the fraction remaining, meaning the fraction of whatever you started with that are not yet decayed, is equal to 1/2, hence the name half-life, to the power of the elapsed time over the half-life time. And so if the half-life is, say, 10 years, right? And then in 10 years, you'd have a elapsed time of 10 years over 10 years. That's 1/2 to the 1 power is just 1/2. If, however, you did 20 years, right? So then it would be 20 years over a half-life of 10 years. That would be to the power of 2, and 1/2 squared is 1/4. I would expect after 2 half-lives to only have 1/4 of my original sample remaining. So here is the final poll everywhere survey question for this particular discussion. Carbon-14 is actually a radioactive element that gets used to characterize the age of lots of things. It's found in Earth's atmosphere, and then it gets trapped in various materials. And carbon-14, given enough time, decays to regular old carbon-12. So if you can find a sample and you find out how much carbon-12 versus carbon-14 you have in it, you can actually use that information to get a pretty good estimate of when that material was formed. So let's say you were studying an artifact that was 2,000 years old. What fraction of the carbon-14 would remain undecayed if carbon has a half-life of 5,730 years? 0%, 21%, 50%, 79%, or 100%. You can calculate this if you want to plug things into the equation on the previous slide, but you should be able to actually think about the mathematical nature and the definition of half-life and get the right answer without actually having to do any number crunching. So there are two types of nuclear events that we want to define, fusion and fission, and you may have heard both of these terms before. Nuclear fusion is the process of two or more elements having their nuclei combined together to form a new kind of nucleus. And so multiple nuclei are forming another heavier nucleus because it's going to have more total nucleons when you're done. So this is thought to happen and actually release energy for any element that's in the top part of the periodic table that has a mass of less than iron. So iron's somewhere there in the middle of the third row, fourth row. I'm forgetting my periodic table, but it's in the 20s on the periodic table. So here is a picture, artist depiction of two sort of unusual nuclei. They'd actually both be hydrogen nuclei. Hydrogen has one proton, but most hydrogen has only one proton and no neutrons. However, every once in a while you can get hydrogen that has one proton and one neutron. That's called deuterium. You could also get hydrogen that has one proton and two neutrons. That's called tritium. And if a tritium nucleus smashes into a deuterium nucleus, you can actually get it to form a helium atom, two protons and two neutrons, release some energy in the process, and also release a neutron if you're doing the counting from the left side to the right side. For nuclei that have a mass more than iron, so the lower 2/3 of the periodic table, it turns out that fusion takes more energy to make it happen than it takes energy and net energy to make it happen. So you got to put energy into that system. So there are people out there actually that are working on this cold fusion. Some people see cold fusion as this white whale of physics that will never be achieved. Other people think that it can happen. But the basic idea is, could we combine light elements, some of which are very abundant around us, in a way such that we actually capture the energy that's released when we put two light nuclei together to form something that's a little bit heavier? And if so, this could be a source of a massive amount of energy. It's just, can we do it? Can we technologically pull it off? Nobody really knows yet. Nuclear fusion does occur naturally in stars, though, and it has been achieved, again, by people, but not in a completely controlled fashion that you're going to be able to just have it as a power source in the corner of your house yet. Fission is the opposite. So fusion is putting two nuclei together. Fission is breaking nuclei apart. And there's two inherent problems in a nucleus. Number one is if you get too many protons packed in there, you have too much electrostatic potential energy. So if I have one proton, it's fine. But the second proton that I put in there, it takes work to get it in there, right? And they're going to store electrostatic potential energy because those two protons ultimately want to push each other apart. Third proton, even more electrostatic potential energy. So some of these things down in the lower part of the periodic table have tens and tens of protons. That's a lot of electrostatic potential energy that's stored in the nucleus. Again, it's overcome, right, by that strong nuclear force holding things together, but things do get inherently unstable. Turns out too many neutrons also make a nucleus unstable. So the neutrons help, they act as a buffer, I guess, in this system to some degree, but you can't have 50 neutrons to every proton. That's also an unstable arrangement. And so there's sort of this tenuous balance. In the top part of the periodic table, most of the elements have roughly the same number of protons and neutrons. But as you go down the periodic table, if you've done some chemistry before, you get far more neutrons than protons and also more of the unstable elements down there with the heavier nuclei. So large nuclei actually have a tendency to split apart spontaneously. Now, this may be spontaneously with a half-life of thousands and thousands of years, but still, lots of these things are inherently unstable. In fact, lots of those at the bottom of the periodic table are man-made elements that people have made in nuclear labs, but they have half-lives of small fractions of a second. So these materials have only existed for very brief windows of time, and they're unstable and they break apart pretty quickly. But nuclear fission of things you can find in nature was the principle actually that was used in developing the nuclear bombs in World War II. So we want to talk briefly about how that process happens. So if you want to build a bomb, and don't worry, I'm not revealing any state secrets here. There's a lot of engineering that would go into this that you would need to know, but you need 4 things to make an atomic bomb. You have to have a material or something that serves as a neutron source within the bomb. And that neutron is going to ultimately trigger the explosion, as we're going to see in the simulation here. You have to have fissionable material in the bomb as well. Nuclei that will break apart when they're hit by something, and that breaking apart will trigger more breaking apart. You need to also have a fission that happens that when you break apart a nucleus, it releases more neutrons than came in to cause it in the first place. If, for example, you make a fission event occur with 1 neutron, and that event just releases 1 neutron, that 1 neutron might trigger another fission event, and it might trigger another fission event, but those are all, sort of random chance, and at some point you probably will miss one, and you won't have any sort of exponential growth of things here. Whereas if one event triggers the release of 2 neutrons, those 2 could create 2 more fission events, which each release 2 neutrons, which could create now 4 fission events, and you can see how that could have the possibility to grow very quickly. It's also going to grow very quickly if you have a large density of these nuclei. They're all packed in a close space. If they're spread out, again, the odds of a neutron from one fission event finding a nucleus of another atom and breaking it apart go down the more that this material is spread apart. So there's a second simulation in the FET website that's called, I believe it's chain reaction, maybe I'm wrong on that, that gives you this simulation of how fission occurs. And I again captured a movie of this. You're welcome to play around with the simulator following the link there. So in this one, it starts out with, I believe, a uranium-235 nucleus, which was the material used in one of the atomic bombs. It briefly absorbs a neutron from this little neutron gun, turns into uranium-236, and then breaks apart into 2 daughter nuclei. And importantly, did you notice? It releases 3 neutrons in the process. So then the suggestion of the experiment was to go to this chain reaction tab where we have a whole bunch of uranium. I've now made uranium that's like man-made uranium. This is about 99% uranium-238 and 1% uranium-235, the radioactive break-apartable stuff. So you'll notice as I fire my neutron gun around here, it mostly just gets absorbed by this uranium-238. And here I hit the uranium-235. So I got my 1 to break apart there, but its other neutrons, if they were absorbed, just turned a uranium-238 into uranium-239. Stable material. I don't get any chain reaction happening here. So now I'm going to make, or simulate rather, refined uranium. And the way I do this is I'm now going to put in 99% uranium-235, 1% the no reaction uranium-238, and notice that when I hit just one of these, it breaks apart, releases 3 neutrons, triggers many, many more. In very short order, I have all of my uranium-235 that have undergone this nuclear fission. Finally, I can put a containment vessel in this simulator and change its size. So I'm going to start out with a small one. The small one only allows us to pack a handful of nuclei in there. I'm doing all uranium-235, assuming the refined stuff. And so you see I get those fission events to occur, but not enough to produce enough energy to make this bomb-like. So this one gets about 40 of these things in here. Still not in this simulated world large enough to make this happen, but in the simulator, if you make the bomb large enough and pack enough purified or refined uranium in there, I trigger enough of these chain events that I release an enormous amount of energy, and this has now created the simulated atomic bomb. You may notice in the news that, of course, the United States is a nuclear power in the world, and there's a handful of other nuclear powers in the world, but every once in a while there's a lot of hand-wringing and what should we do about, will this country or that country become a nuclear power? Largely what they're trying to track is how good are the refining capabilities of those countries, because uranium can be had, but to produce uranium or another material to make a nuclear weapon, you need to refine it enough that you have the radioactive form, at least in the dominant material in that. And so, that's always part of the game, is how do you refine uranium, and how good does that other country across the way have capability for you refining uranium. All right. So let's talk a little bit about the 2 atomic bombs that were used in World War II. They had 2 different engineering designs, but both ultimately achieved this nuclear fission. And so the one on the left is, I think this was called the Little Boy, I can't remember exactly, but it had a core of uranium-235, this radioactive uranium. But they were kind of genius about this. If they put the whole core in there right from the get-go, it would have a critical, a critical mass to trigger that chain reaction and explode right out of the gate. So instead, what they did is they engineered essentially a ball with a hollow core taken out of it. So there was a hole in the middle of the uranium-235, and that was enough to keep it from having a spontaneous chain reaction when it was missing its center. There weren't enough uranium-235 nuclei close enough to other uranium-235 nuclei. Then they manufactured a plug of uranium-235, just the size for that hole. I don't think they tested it out, but they built it so that when you triggered this device, the explosives shot the plug into the hole, filled the gap in there, and now you had a sphere of enough uranium-235 in enough space that there was this critical mass at critical density that triggered the chain reaction and the subsequent explosion. The other device was a different engineering style. So this one used the core of polonium-239, again, another radioactive material that will release a lot of energy through these triggered chain reactions. But what they did is they made this polonium-239 so it was at a low enough density that it wasn't at this critical state yet. And that was the core, surrounded by the uranium-238, and then a wall of high explosives. And so actually when this bomb exploded, the explosives compressed that whole center core. And so now the sphere of your polonium-239 got smaller, didn't get less particles in there, so you're pushing all the particles closer together, and that got those nuclei close enough together that it triggered, again, a chain reaction with that device. So there was a lot of, scientific effort that went into this, and people had opinions one side or another, but it was a very sobering project for many of the folks that worked on it. This is Robert Oppenheimer, who was the chief scientist on the Manhattan Project, who was reflecting on that experience after World War II. And here's what he said about it.
5, 4, 3, 2, 1.
In the dead silence of the morning, at 5:29:45 Mountain War time, the Jornada del Muerto was bathed in an intense flash of a light that man had only seen from the stars.
Not be the same. Few people laughed. Few people cried. Most people were silent. I remembered the line from the Hindu scripture, the Bhagavad Gita. Vishnu is trying to persuade the prince that he should do his duty. and to impress him takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds." I suppose we all thought that one way or another.
So that's what we wanted to talk about in this particular lecture, the process of nuclear fusion and nuclear fission and how ultimately those produce a release of energy that can be used to release energy for other purposes, but can also be used to release energy for the purposes of building weaponry. Fusion is the process of joining together multiple nuclei. Fission, the process that we actually achieved and was at the root of the devices used in World War II, is the breaking apart of large nuclei and the release of energy along with that. And when you have any sort of radioactive element, they get characterized by something called the half-life, the amount of time it takes for half of the nuclei in a given sample to radioactively decay. And nuclear bombs require that you have this chain reaction. So you have one fission event, but that one fission event needs to trigger subsequent fission events. Those trigger subsequent fission events. And you need, again, if you want to release a large amount of energy really quickly, you need many, many triggers up the line of increasing number of fission events in the critical mass of material that you've packed into the center of your device. If you haven't done so before, I'd encourage you to read section 1 in chapter 15. This is where our textbook author talks about the same stuff that I did, but as always includes some additional detail that I didn't have time to get to here. I would recommend that you work on the chapter 15 recommended practice problems if those have been helpful for you. And if you want to take a look ahead to what we're going to talk about on Wednesday, that is section 2 in chapter 15 in the text.